All right, so here is a device to produce vibrations. It consists of two counter-rotating wheels with offset. Each has a mass of 1 kilogram, and it's offset by a distance of 12 millimeters. The wheels are synchronized so that the vertical positions of the unbalanced masses are always identical, right? So they get to the top at the same time and so forth. So they're always in alignment. So they're causing pretty much the same up and down motion. But you would double the amount of force that one would have done because there's two of them. The total mass of the device, so it's like kind of a big M, is 10 kilograms. And determine the two possible values of the equivalent springs, right here, constant K, for the mounting, which will permit the amplitude of the periodic force transmitted to the fixed mounting to be 1,500 newtons due to the imbalance of the rotors at a speed of 1,800 RPM. So we need that right here. So we got omega, I guess I'll call it omega F, 1,800 RPM, but we're going to change it to 2 pi and divide it by 60 and turn it into a natural frequency of, not a natural frequency, a forcing frequency in radians per second. Okay. And we're working backwards here so that we also have FT, transmitted load, 1,500 newtons. Now, we define what the forcing value has to be, right? So the forcing value, sometimes we call it PO, sometimes FO, but it's going to be mass times eccentricity times operating of radius per second squared. But then we have to remember there's two of them, right? Because there's 1, 2, and they're synchronized to each other. So they'll be happening at the same time, which is what synchronized means. So 2 times 1 kilogram, right, is where the mass is 1. Eccentricity is 0.012, that's in meters, and we have 188.5 is the speed at which it's operating. We get 852.8 newtons is how much we're saying that this stuff is putting into the onto the piece. Now, so our transmission ratio, TR, is 1 over R squared minus 1. We need to look that up. It's true. So wait a minute. We need it though. The transmission ratio, we need to find it. It's going to be FT over, I'm calling it FO. Some people are calling it PO. So that's 1,500 divided by 852.8. So the transmission ratio 1.759. So what we could do is we could find out what that R squared is going to need to be. And so if we do that, R squared minus 1, and that's plus or minus right there, is going to be equal to 1 over 1.759, which is 0.5685, I think. Looks like a 5. Maybe it's a 5. I hope it's a 5. So we have that R can be equal 1.252 or 0.6569. That R will accomplish both things. So now we know what the natural frequency is. Do we know the natural frequency? Yeah, we can find them. Right? We find the 2 different natural frequencies that would allow for this, right? That would limit the forces onto that thing. And so our natural frequency is going to be omega F divided by R, or 188.5 divided by which one did I do first? I did the lower one, 0.6569. And I got 287.0 radians per second. And then let's call it 1, omega n, 2, omega f, we'll call it R's, remember them, 188.5 divided by 1.252, with 150.5 radians per second. Ran out of space, so I'm going to the next page with purple. I already did purple, man. You got a purple fascination. You're gonna run out of it. See what I did there. Okay, so with that, we know that omega n is the square root of k over m. So we can say k is equal to m times omega n squared. So that first one is going to be, what did we say the mass was? Well, they had the total mass. This one should be the total mass. That should be like capital M. Total mass is 10, and omega n is, let's see, 287 squared. So we look at that one, and we get 823.5. And by it gets big, right? So you have to be careful here. These are, so I went ahead and turned them into kilonewtons per meter, right? So if we come back to there, we get, oh, here's the number right there. And then we do the second one right here. Let's say K2 is going to be equal to 10, and that's 150.5 squared. And it comes out to 226.5 kilonewtons per meter. And boom. That's the other one, 227. So we got the right answer. Yay for us. We did it. So Dora the Explorer. Let's try another problem.